So yesterday, we were going over standing waves. Okay? We didn't get to air columns. We were just looking at standing waves that travel in like a spring or something like that, or a bridge, okay, in a bad case scenario, something like that. So what I would like you guys to try, okay, in terms of like standing wave stuff, okay, is I would like you to try questions 3 and 4 here. Okay, hand these up over there and make this a little bit bigger. Okay, try 3 and 4 based on what we learned yesterday about standing waves and see how you do with it. All right, I'll give you guys a few minutes on that and then we'll kind of go over them together here. Right. So on number 3, okay, we're told that a standing wave is in a spring that's stretched to a length of 6 meters. Okay, so basically the distance from here to here is 6 meters. The standing wave pattern consists of 3 antinodes, so sometimes it's useful to just draw it out. Okay, so this distance here, how does that and the picture I just drew help me?
You can figure out the wavelength.
Exactly, I can figure out the wavelength. How many wavelengths are there in that picture? 1.5 wavelengths. Okay, so I know that 6.0 meters equals 1.5 times lambda. All I have to do is divide 6 by 1.5 and I'll get lambda. Is it 4? Yeah, okay. Okay, so lambda is now 4 meters. Okay, well that's useful because now I also have the frequency, 2.5 hertz. V equals F times lambda. 2.5 times 4 should be 10 meters, right?
Yeah.
Or 10 meters per second, actually. Speed. Everybody all right with that one? Some people have done number 1.
How is that wave 3 antinodes? Isn't that 4?
1 antinode, 2 antinodes, 3 antinodes. The antinodes are the constructive, the nodes are the destructive.
Yeah.
Yeah, there's always one more node than there are antinodes.
I was looking at the others.
Okay, how many people have done 4? Okay, I'll give you a few more minutes to get done number 4, and then we'll have a look at that one. Then we're going to talk about air columns. Get my air column ready. Okay, so on number 4, okay, we have a spring attached to that is stretched to a length of 8 meters. So we know that the distance from here to here is 8 meters. Okay, the speed of the waves in the spring is 5 meters per second. And the simplest standing wave pattern is this. Okay, we learned that yesterday. That's the simplest standing wave pattern I can make with a spring. So how many wavelengths is that? 1/2. So how long is the wavelength? Double that, right? So it's 16 meters, right? So I know that lambda equals 16 meters. I know the speed is 5 meters per second. So I can calculate the frequency. In this case, which frequency? What do we call the first frequency it will produce? The fundamental frequency. Okay, so F is going to equal V over lambda. Okay, so that's going to be 5 divided by 16, which should give me 0.313 hertz. Okay, now what a lot of people do when we're just starting out with standing wave kind of questions is they do a lot more work than necessary for the next question. They redraw the diagram, okay, they do all that kind of stuff, but they don't have to. That's F1. F2 is how many times bigger than that? 2. That's the next frequency you would get, so you just multiply that by 2 and you get 0.625. Because it's actually 0.3125 when you actually do the calculation. All right, everybody okay with that? Okay, so if a question ever has a part B, and trust me, standing wave questions often do this, either with a standing wave or an air column, which is still a standing wave, okay, they'll ask you, what's the next frequency you would see if it's a spring? What's the next frequency you would hear if it's an air column? Okay, everyone kind of follow me there? So that's something to know. Okay, and that's where it's just testing. Do you remember that F2 is 2 times F1 and F3 is 3 times F1 and so on and so on. Okay, let's have a look at air columns. So in our wind instruments, vibrations produced by lips or reeds can be used to produce certain notes by changing the length of the column of air which they vibrate. Okay? Air columns come in two types, open and closed. Most musical instruments are open air columns, and there is a very good reason for that. Open air columns have a wider range of frequencies at which they will oscillate, which will give them a wider range of frequencies they can produce. Closed air columns only resonate at odd numbered frequencies. Sorry, that's not true. They resonate, but they don't make sound. They only make sound at odd numbered frequencies. They resonate, but don't make sound at even numbered frequencies. So F1 will make sound. F2 won't. F3 will. F4 won't. Okay, I'm going to show you why here in a minute. Now, the column of air is not completely closed in a closed air column, so the name's a bit misleading. It's only closed at one end. An open air column is open at both ends. Okay, so if you think about how a musical instrument works, okay, you usually have other places for the air to escape. Okay, and so you're essentially got two open ends to a column of air. Everyone follow on that? So the first type we're going to look at are closed air columns. So there's an end that is closed, and that acts as a reflective surface. So does the inside of the tube that's resonating, but when you have one end that's closed, that's the primary reflector. Okay? And so you get standing waves reflecting off of that rather than off the inside of the tube. With an open air column, it's much more about reflections within the tube itself. So for this closed air column, our first frequency that we will hear is F1. And the waveform that gets produced in there looks like this. Okay, so this is F1, our fundamental frequency. How many wavelengths are in that tube? A quarter of a wavelength. Okay, because remember, for a standing wave, one full wavelength looks like that. There's only that much in the tube at F1. Right? So if I know the length of the tube or the length of the column of air, I know the wavelength, because it'll be 4 times the length of the tube. Okay? And that's where this formula comes from. For closed air columns resonating at their fundamental frequency, the length of the column of air multiplied by 4 will give you the wavelength of the sound. Okay. Everybody all right with that? Okay, now that's the first place that column will resonate. If I lengthen that column, I can get it to resonate at other points as well. It'll sound the same, but there'll be different places. I lengthen the column because I give it more room to set up the standing wave. Okay? The standing wave is a certain length. It's got its wavelength. But if I lengthen the tube, I can get more wavelengths in the tube. And there will actually be resonant points along the length of the tube. I'll demonstrate without hopefully making another mess. Okay, so I'm going to have a tuning fork. Okay, and I'm going to pick, no, I don't like that. I'm going to pick F. I don't know why, I just picked it. Okay, and the frequency of this F note is 349.2 hertz. Okay, and all I'm going to do is fill my column, oddly enough, up with water. Isn't this supposed to be about air columns?
All air and water, fluids.
It's true, but I'm actually going to use the water as my closed end. It's going to reflect off the water, right? But I have to have my tube full first. sounded like it was getting close to the top. Why does the sound change as I fill it up?
Because there's lots of air.
My air column gets shorter and shorter. Okay, so now I've got this tube within a tube, okay? The white PVC tube is gonna be my column of air. All I'm gonna do is pull it out of the water, okay? As I pull it out of the water, the length of the air column gets longer. And I can measure the length of that air column because on the pipe, there's a ruler. And all I have to do is measure it to the water, and I'll know how long my column of air is. Everybody okay with that? Okay. So, see, I'm trying not to move it very much. Okay, did you hear I got louder there? Okay, so that's my first resonant point. And it's at, try not to move it too much here. 23 centimeters. Okay, so my first resonant point is 0.23 meters. We used to do this as a lab, and what happened to me was, like, I don't know if you guys noticed, but I was totally flustered by that because I used to make a joke about that happening to people when we did this as a lab, because they would put it on top of the desk, and then they would lift it up. Where do you get wet? Yeah, there were lots of people who were walking around looking like they'd wet their pants. Yeah, because this would spill right here. It was funny the first few times, and then it was kind of not funny anymore. That's hence the taping job on the model. So yeah, so 23 centimeters is our first one. Okay, we'll see where our second one is. Where should it be? Okay, right now, that first resonant point, how many wavelengths were in the tube? A quarter. Okay, my next resonant point should be a full half a wavelength further away. Right, that's where the next antinode would be. Okay, because if I just start this from the very beginning, okay, there's another one right there. I don't know if you guys can hear that one as well. Okay, we'll get it again here, but there's like loud, quiet, and then loud, quiet as I go along. Okay, the quiet point is halfway in between the two loud points because it's where the node is. Okay, that's that when I hear that really quiet point, there's a node at the top of the tube. Okay, so my next one is actually 3/4 of a wavelength away. So that first distance I measured is 1/4 of a wavelength. So the next point I hear should be not twice that far, but 3 times that far. That's 1/4. My next resonant point should occur at 3/4. So it should be 3 times further than that. Okay, which should be about 69 centimeters. Well, isn't it awesome? 70. Okay, now I wasn't really on the ball here, so we'll remeasure and see if I was just off a little bit. I made it worse. 71, okay? But maybe the first one was off a little bit too. We can recheck the first one. Maybe we'll just do that. Make sure I did the first one right. Okay. Let's go straight on 23. Okay, so, I mean, there's going to be a little bit of variance there. It's me judging, too, where was exactly the loudest point, because there's about this much room.
It was 24, you moved it.
I let it drop, and then I pull it back up. So we'll try it again.
Yeah, it was
24?
24. A bit in between.
Still 24?
Yeah.
Okay, so we're 24. That makes it better. So we had 24 and we said 71, right?
Leaking.
All right. All right. Next one's at 5/4, so that would be, yeah, it might be long enough for us to get the last one. Okay, I'll probably have to stand on the chair in order to get the last one. All right, so hey, Luke, I'm going to have you read it because I won't be able to read it if I'm standing on the chair. Okay. That's 70, right? Okay.
It's up.
No?
Yeah.
Just out there.
Now it's like 20 or 100.
120?
It should
About right. Yeah. Okay. Sneaking fast. If I carry 3, I'll have to fill it again. Maybe I shouldn't put it there. I'll dump it out later. But not much later, or I won't have to dump it out. Okay. So, we said this one here was 120, right? 1.2 meters. Okay, so if I calculate the wavelength for those 3 numbers that I just got, should I get around the same wavelength? Okay, so if I multiply this one by 4, that should give me the wavelength, right? And it's going to be, we said it was 0.24 when we redid it. Okay, so multiply that by 4, and we're going to get 0.96. Okay, and then this one here, 0.71 meters, equals 3/4 times lambda. So if I divide that number by 3/4, 0.95? Ish, yeah. What does it come out to? Not ish.
0.946.
Okay, and the 1.2 meters equals 5/4 of a wavelength. So if I take the 1.2 and divide by 1.25, I'm feeling pretty good about this number.
0.96.
See, this is why physics is awesome. Okay? If it catches on fire or explodes, it's chemistry. If it's green, it's biology. And if it works, it's physics.
But fire is fun.
Oh, I'm not saying fuck, well, that's a little scary. Okay. Keep my eye on it. Okay, so 0.96, 0.946, and 0.96. So we're going to say the wavelength here is 0.96. And we got 2 where that was the case, so this one might have been a little bit off here. All right, so our wavelength is 0.96, and I know the frequency of the sound. What can I calculate now? I can calculate the speed of sound in here. Okay, so V equals F times lambda. If I take my 0.96 and I multiply it by 349.2, I'm going to get a pretty darn reasonable number. 335.232 for the speed of sound in air. Now, that formula you have, that's 332 plus 0.6 T, is not going to give us that number, but we're at altitude. Okay? And at altitude, the air is thinner, which also is going to affect the properties of air, and thus the speed of sound waves through air. Okay? So getting 335.232 as the speed of sound in air for this room is a pretty good number. Okay? Like that's a very, very reasonable number for us to get here. All right, so is everyone kind of following how that works? Okay, so this is, anytime I get an actual resonant or loud point when I'm doing this, what part of the wave is at the top?
I just had a question about the frequency.
Yeah.
What did you get? 329.2?
It was on the tuning fork?
It was on
Yeah, yeah, there's no way for me to calculate this on the tuning fork makes that sound. Yeah. Okay, so what part of the wave is at the top of the tube every time I get one of those loud points? An antinote. Okay, this is F1. This is F2. Sorry, this is F3, sorry. This is F3, this is F5, this is F7. Notice that it goes along with the quarters of a wavelength that are there. Shouldn't this resonate at F2 and F4 and F6? Well, it should resonate, but it's not going to make any noise, because at the next wavelength, if there's one quarter in here, the next resonant point, F2, the waveform, is half a wavelength. But what's at the top now? A node, and there's no vibration at a node. Okay? There's still a wave in the tube, but because there's a node at the top, we don't detect any sound. It's complete destructive interference. Okay? That's what reduces the range of frequencies that a closed air column can produce. So if you're, in a moonshine band and you're blowing over the top of the moonshine bottle, you're not producing a lot of different frequencies. I mean, through the night you will, because there'll be less and less shine in the bottle, but you don't have the same range. And all you're ever producing is the fundamental with that, because you're always producing a sound with 1/4 of a wavelength in the tube. Okay? Everybody with me there? All right, so the formula you have, and this is on your formula sheet, is that for a closed air column, lambda equals 4L. It doesn't say closed air column on your formula sheet. That part you have to remember. You're not typically going to be given a question that says, this closed air column is resonating at F5. Okay, now calculate something. It's not going to do that. Okay? Most of the questions will involve being at the fundamental frequency. So you can use that formula. A part B might involve something other than the fundamental frequency, like maybe calculating what's the next frequency that you would hear. Now, if I asked you that about a closed air column, okay, a very common mistake people would make is that if we calculated that the fundamental frequency for this column was 350 hertz, let's just say it was 350, so it's a nice round number. What's the next frequency you would hear? If F1 is 350, what's the next frequency I would hear? Okay, let me put it a different way. I can hear F1. What's the next frequency I'll hear? 2 or 3? Okay, so 3 times 350 is what, 1025?
Aren't we hearing the same note every single time?
No, I'm saying if I keep that column the same length,
Oh.
and I put different frequencies on, what's the next frequency of sound that length of column can actually make resonate? It would be a shorter wavelength, right? So yeah, the next frequency I would hear is F3. I won't hear anything at F2. Okay, everyone all right with that? All right, because what we did here, what we did with the tube there is not the same as what this diagram is showing. Okay, I know I wrote on here, but okay, what I was doing was this column was 0.24, this column was 0.71. On the diagram, they're all the same length, and they're using different frequencies. Okay, that's why there's more waves in the tube. Okay, what I did was lengthen the tube. Right, so if I was actually drawing this experiment out the way I did it, I'd have 0.24, right, 0.71, and then much longer for the 1.2. Okay, that's the way we did it, but on each one of those, okay, yeah, we had this, and then we had, whoops, I screwed that up. Sorry, my anti-node got really big there. What a mess. Let's try that again. Okay, so should start from the bottom. That makes more sense. Okay, and so on and so on, right? Okay, everybody okay with how that one worked? All right, now open air columns work a bit differently, because they don't have a closed end to bounce off of. So instead, you get reflections along the length of the tube. Okay? And you get this. they'll resonate at all of the frequencies. F1, F2, F3, F4. There's no dead ones because there's never a node at the top. Okay? It's always antinodes at both ends when it's resonating. Okay? Now, here's what's different. The fundamental frequency in a closed air column had a quarter of a wavelength in the tube. How much of the wavelength is in the tube for this one? Half. Which is why the formula for open air columns is that the wavelength for the fundamental frequency is 2 times the length of the tube instead of 4. Okay? And every resonant point, instead of being 1/4, is now 1/2. I mean, granted, the resonant points that actually made noise in the closed air column are also still a half a wavelength apart, because that's how far antinodes are apart. Okay, but here it's actually each resonant point again half a wavelength apart.
Couldn't you still have a node at either end of the column? Like this, if you move the whole diagram, like at half a or quarter node.
Oh, yes, yes, sorry, you could, but we wouldn't get any, like it wouldn't be one of these numbers. It wouldn't, this is F1, this is F2. None of the actual frequencies produce, like none of these resonant frequencies have nodes at the top. I could make the tube long enough that I had a node at each end and I wouldn't hear anything. Okay, but in this case, all of the resonating frequencies result in an antinode at the top. Sorry, I worded that poorly. Yeah. Okay. All right. So these ones, the problems are going to be worded similarly. They're going to give you the same things: length of the tube, speed of sound and air, or the frequency, or something like that, and ask you to calculate the length of the tube. Or they'll give you the length of the tube and ask you to calculate the speed of sound. Okay, but the only thing that'll change is the question will start with a closed air column or an open air column. Essentially, what you do is the same. You just use this formula for open and 4L for closed. Okay. Other than that, they're pretty much the same thing. Okay. All right, everybody good with that idea? Okay. Yeah, you know what? Their examples are so bad. I want you guys to try this one, and then we'll walk through it together, see how we do on it first. Okay, so you have a closed air column. It's resonating at its fundamental frequency of 256 hertz. We want to find the length of the air column. So remember, it's a closed air column. Lambda equals 4L. And it tells us it's at the fundamental frequency. Okay, so for this one here, okay, we know that this is our situation. We have a closed air column resonating at its fundamental frequency, so that means that 1/4 of the wavelength is in the tube. We know that fundamental frequency is 256 hertz. Okay, we're looking for the length of the air column if the speed of sound is 343 meters per second. All right, so I have V and I have F. What can I find with that? Wavelength. Okay, so wavelength equals V over F. 343 divided by 256. All right, so my wavelength's 1.34 meters. But I'm going to keep all my decimals there. All right, now I should be able to find the length of the column. Okay, by simply taking my wavelength and multiplying by 4. So times 4. Okay. Dividing by 4, not multiplying by 4. Okay. Can I go home yet? No? Okay. All right, there we go, 0.335. Been that kind of day. All right, everybody okay with that one? All right, I'm going to put a open air column up here. There we go. Oh, that's bad luck. Okay, but try that one anyway. We'll round it. 0.67 meters. Probably should be rounded anyway. So for this one, we have this open air column. Now it's still got a fundamental frequency of 256 hertz. Okay, and we're looking for the length of the air column, which is lambda equals 2L. Okay, and we know that the speed of sound is 341 meters per second, so it's just like our closed air column question, which is what I told you, right? Like the wording, the setup, everything's going to be the same for these. You're just going to use 2L or 4L depending on what type. So I'm going to calculate the wavelength, 341 divided by 256, okay, which is still going to give me that 1.35 or whatever it was on the last one, because it's, oh no, it was 343 on the last one, wasn't it? Okay, 341 divided by 256. Okay, so we got 1.33 meters. Okay, if I want to find L, it'll be lambda over 2, okay, and that'll give us our unlucky number. Okay. All right, everybody all right with that one? Okay. I would like you guys to try on that, on the worksheet here. So we've done 1 and 8, and I'd like you to do the other ones here. So do 2 and 2 to 13, obviously minus 8 because we already did 8, right? And if there's any ones that give you trouble in there, we can go through them together. Let's go over it now. Okay, so the couple of reminders we got are as follows. Your unit exam review package will post tomorrow in Google Classroom, so you can look at it over the weekend. The only thing we will not have covered by the end of tomorrow will be Doppler effect. Okay, so that's really all that's left, and we may even get to a bit of that. Actually, tomorrow we're going to do a Hooke's Law thing. So Monday we'll do Doppler effect. Okay, we might need a little bit of time on Tuesday to finish that, and then Wednesday I'll actually do the in-class review, and then Thursday will be your test. Okay, Friday we'll go over the Unit 4 exam, and then the next week, Monday Unit 1, Tuesday Unit 2, Wednesday Unit 3, Thursday you come with questions. Okay, I'll answer all the questions that you bring that day. Okay. In terms of like review stuff and help sessions and things like that, obviously during class I've got the same help sessions I always do. I still don't have a supervision or room use schedule for during exams, so I cannot tell you when I will be available for help during exams. My room gets used a lot during exam week, so I don't know how available it or I will be. Okay? But thankfully, we have lots of chances to review and ask questions before exam week starts. But I realize you're probably not prioritizing physics as it's likely your last exam. Okay? And that's fine. Just know that I don't know how available I'll be for help during exam week. Okay? You have nothing else to hand in to me. Okay? The simple harmonic motion assignment was the last thing I'm taking in for marks. We're just doing the Hooke's Law thing tomorrow. It's just kind of a demo because we didn't get a chance to do it earlier, and we have time, so we're going to do it. But we'll just end in class thing. We won't be handing it in for marks. Your last chance to hand in any overdue assignments is June 16th at 3:20. Okay, that's the last day at the end of the day. Okay, if I don't have it by then, I won't be marking it. Right, so make sure you have it in by then if you have anything overdue that you would like to have graded and added to your final grade. Okay, remember that the arrangement for your final exam will be that it is no fault. You cannot do worse, but should you do better, which is very likely, it will replace your course mark. Okay, so in that way, it is possible for anybody to get 100, which is a pretty sweet deal, really. Okay, you know, if you made one mistake along the way during the course, you can't get 100, but now you can. Okay, it's possible. So take it as a challenge and also as an opportunity. Okay, because it is a big opportunity to do better and raise your grade. Okay, so we will do that. Any questions from you guys? Okay, we'll leave it at that.